Greetings. So we had some discussion on the phase shifts and what kind of information they bring to us when you perform a collision experiment, and in particular we saw that when you have a phase shift, and what it does is here, so this phase shift will change the position of the nodes of the radial function. This is what we discussed last time, that nodes of the radial wave function are either pushed or pulled depending on whether the potential is repulsive or attractive, with reference to which the phase shift is either negative or positive. So when the phase shift is negative in the case of repulsive potential, then the nodes are pushed away, otherwise they are pulled inward. Inward is toward the center of the scattering potential, and this is the general picture that emerges, and we clearly see that the phase shifts carry valuable information about the target potential itself. Now what we will do is to analyze the formulation a little further, and the phase shift we know is an angle, and typically angles are known modulo pi. So if you add or subtract pi in mathematics, usually you are not able to see the difference, because there is just a sign inversion of various terms which come in, and it is not modulo pi. So you can add 2 pi, 3 pi, 4 pi, 5 pi and so on, and you really do not get any exact idea about what the actual phase shift is. An absolute value is something that you would like to define, and there is a way of doing it by introducing a mathematical construct. So let us introduce a coupling parameter like lambda. Okay. Now this is not a physical switch, it is not like a rheostat or some regulator that you have to control the strength of the interaction, because the strength of the interaction is determined by nature itself. But this is a mathematical construct, and you define the potential such that you introduce a parameter lambda on which you have got a mathematical control, and you can now talk about two different potentials, one with a value lambda and another with a value lambda bar, and this potential we will indicate by a u bar. So a bar on top of it is the potential, this is the reduced potential, mind you. So this is the reduced potential corresponding to the control parameter lambda equal to lambda bar. Now this relation is valid for the tangent of the phase shift. We derived this in the previous class. We will use this now, and we will now have a similar expression not just for the potential u, but a similar expression for the potential u bar for exactly the same reason. So you will have identical relations for u and u bar, and if you take the difference, you get the difference between these two tangents. Okay, and the difference in the phase shifts delta and delta bar, or rather difference in their tangents, is then given by this integral in which you have got the functions u and u bar. Okay. So what you can do now is to divide this difference by delta lambda, which is your control parameter, and then you can take the limit delta lambda going to 0. So you will get the rate at which the phase shift, or rather the tangent of the phase shift, changes with your control parameter. So now we take the limit delta lambda going to 0, and that gives you the derivative of the tangent of the phase shift, and this is the only parameter, u is the only thing which depends on lambda. So you get the rate at which the potential will be changing with respect to lambda in the integral. So this appears in the integrand. Now you take the derivative of the tangent function and you get the derivative of the phase shift itself with lambda, with the 1 over cos square term, and cos square delta for small angles it will be nearly equal to 1 if the phase shift is very small. So, if you move this cos square function over here, you can approximate this bracket nearly equal to 1. So, you get a relation which is approximately correct, very nearly so for small phase shifts, that the derivative of delta with respect to lambda is given by this minus k times, this is a factor of 1, and then you have got this integral, right. Now, notice that lambda is just a mathematical strength parameter, but when you do the calculations you can assign a certain value to it, okay, when you simulate this in a quantum mechanical model, and then you can introduce a coupling parameter, and this function, which is the function corresponding to the potential to the unbarred potential, this is the wave function corresponding to the u bar potential, right, and this function you can expand around y bar, okay, because the wave function, when you have a certain potential, because what you can do is let u bar go to 0, which is no potential at all, which is the free particle, okay. So, if you let one of these go to 0, then the other potential will tell you how the phase shift responds to that potential. So, this wave function, it will not be very different from y bar, and you can take the leading term, and what this gives you is the square of y bar, okay, and you can always choose y bar to be the same as the spherical Bessel function or the solution for the free particle. So, now let us examine this relation. Here you have got a square in the integrand, okay, the integrand consists of this, it is a product of two factors, one of which is a square, which is always non negative, it is always positive, right. The other is the rate of change of the potential with lambda, and then notice that there is a minus sign over here. Now, what this means is that the value of this derivative, if this sign is not changing in this entire range 0 through infinity, then the sign of this d delta by del d lambda is opposite to that of the sign of del u by del lambda. The reason it is opposite is because there is a minus sign here, the other factor is positive, and this its value, it does depend on r, but we are presuming that this derivative of u with respect to lambda is not changing its sign in the entire range of integration, okay. So, d delta by d lambda will have opposite sign. Now, what this helps us is the following, that this phase shift, which is defined modulo pi, can now be defined in an absolute manner, because we can set the value of delta, that angle, to be equal to 0 when u is equal to 0, okay. So, this is like calibration in a certain sense, it is fixing the 0 of the phase shift, and once you fix the 0 of the phase shift, then let that phase shift evolve the way it would, and it will change from 0. So, it will the ambiguity of modulo pi phase shift can be removed by this mathematical trick using this control parameter. So, this is the tangent of the phase shift, and this is the expression that we get for the potential u, and this is the expression which we can really use to carry out our phase shift analysis. So, now let us consider a potential which has got a strict finite range, which means that beyond this range r equal to a, the potential is 0. Now, this is what is meant by a potential having a strict finite range, and many scattering potentials are of a similar nature. Some of them do not have a strict finite range, but they have a range which is not so strict, but nevertheless you can find a region of space beyond which they have practically no influence, because any physical potential does have diminishing influence the farther you go away from it. So, in this case the exterior solution, which is the asymptotic solution, this is the solution as r tends to infinity, right. Now, that is going to be the nature of the solution in the exterior region, and that we already know from the outgoing wave boundary condition is given by a superposition of the spherical Bessel function and the Neumann function, and it is mixed in this proportion which is determined by the potential via the phase shift it generates, or rather the tangent of the phase shift it generates, right. So, this is the radial function in the exterior region, and what we know is that the function and its derivative must be continuous in the entire space, right. The Schrodinger equation is a second order differential equation. So, the wave function and its first order derivative is continuous in the entire space. So, they must be continuous at r equal to a as well. So, inside this region, in the small r region, even if we do not know what the potential is, even if we do not know the exact nature of the wave function, we do know that whatever be the wave function and its derivative must be continuous at r equal to a, right. So, this we can say this in terms of the logarithmic derivative of the radial wave function at r equal to a, that this logarithmic derivative must be continuous at r equal to a, and if you evaluate this derivative in the interior region, it must be the same in the exterior region. We do not have much information about the nature of the solution, nature of the radial function in the interior region, but we do know what it is in the asymptotic region, in the exterior region. So, we can use this exterior wave function to get the logarithmic derivative by taking this dr by dr divided by the radial wave function in the exterior region and evaluate this at r equal to a. So, let us do that, and the derivative of the radial function in the exterior region is the derivative of this. So, this is j prime, prime denotes derivative of the Bessel function with respect to its argument, okay. And since the argument is kr, the derivative then gets multiplied by a factor of k, okay. So, that is how this k comes. So, that is the notation we are using. So, you get this is some energy dependent normalization a caret or a hat, which of course will cancel, and these are the two derivatives in the numerator, and this ratio is evaluated at r equal to a. Now, this energy dependent normalization disappears from our consideration, they cancel each other, and you get an expression for the logarithmic derivative. Now, this expression you can invert by cross multiplying, just manipulate these terms and get the expression for tangent of delta in terms of the logarithmic derivative gamma. Okay, we first got gamma in terms of tan delta. So, we just invert this relationship and write tan delta in terms of gamma. Okay. Now, we are dealing with a potential which has got a strict range, r greater than a is 0, that is a strict finite range of the potential, but there may be potentials which do not strictly go to 0 beyond a, but they have a negligible effect outside a certain domain like r equal to d. Beyond this, even if it is not exactly 0, if it is a negligible effect, then you can still work with a relationship of this kind with a replaced by d, because the asymptotic solution is what we have exploited here. Okay, so, it really does not matter, but for our general consideration we will deal with those potentials which have got a strict finite range just for simplicity, but actually even these potentials can be handled using similar techniques. So, this is our expression for the tangent of delta, and we now define a parameter called Q. I am using the notation from Joe Shane's book. So, Q, this is the definition of Q. Notice that in the numerator you have got obviously a logarithmic derivative, which is what you have in the new denominator also. So, this is a dimensionless quantity, this is the definition of Q, and this is a useful parameter in scattering theory. So, you introduce the parameter Q using this definition and invert this to define gamma in terms of Q. Now, having defined gamma in terms of Q, you insert this expression on the right hand side in this position for gamma, which is in the expression for the tangent of the phase shift. So, let us do that. So, this gamma is replaced by this ratio. Okay. So, I have just substituted this term over here. In the numerator there is a gamma, and in the denominator also there is a gamma, right. Now, you find that there is a k here, there is a k here, and there is a k here, and there is a k here. So, k cancels everywhere, and now you can write the same expression without the k's. Okay. So, k cancels out, and after cancelling k, notice that this Bessel function and this Bessel function will cancel each other. So, JLKA and this JLK will cancel each other. So, that leads to some simplification. Okay. So, this is rather straightforward manipulation of terms, and you get an expression for the tangent of the phase shift in terms of this Q, right. So, this is JL prime KA in the first term, and then there is a JL prime KA in the second term as well. So, I take JL prime KA as a common factor, and then in the numerator I have got 1 minus the inverse of the parameter Q, which is defined. So, this is the numerator. The denominator likewise is given by this term. Now, if you again simplify this a little bit, because there is a inverse Q in the numerator as well as in the denominator. So, the 1 over Q in the numerator can cancel the 1 over Q in the denominator, but when you do that you have to balance the second term, and when you consider that balance, the numerator then becomes J prime J, right, and then you have got Q minus 1, and in the denominator you have got Q times n prime J minus J prime n. Okay. And now, the inverse Q in the numerator and the same in the denominator cancels each other. Okay. So, now we have got a fairly simple relation for the tangent of the phase shift, and now you have got the Bessel function, you have got the derivative of the Bessel function, and then the Q parameter which has been introduced in terms of the logarithmic derivative. Now, let us ask, how does it behave at low energy? Okay. As the energy of the projectile if is diminished, and in the low energy limit as k tends to 0, what is the value of the phase shift? How does it change with energy? What is its energy dependence for small energy? Now, that is the question we raise here. We will also later consider the high energy limits. Okay. So, for now we consider the low energy limits, low energy behavior, and you make use of the expansion of the Bessel function in a power series in z square. Okay. So, the Bessel function for the quantum number L goes as z to the power L divided by, this is a double factorial which is essentially a multiplication. It is similar to factorial except that the even numbers are missing. Okay. So, only the odd numbers are multiplied in this double factorial notation, and 2l plus 1 is always an odd number. So, the last number up to which you carry out this multiplication is 2l plus 1. Likewise, you can also define 2l minus 1, which is also an odd number, and you can take all the product of all the odd numbers and define a 2l minus 1 as well. So, you have the Bessel function, which is z to the power l divided by this 2l plus 1 double factorial term, and then you have got a power series over here. Now, z is your Ka, A being the range of the potential, K is coming from the momentum, and it is determined by the energy. So, in the low energy limit you are seeking the limit k tending to 0. So, obviously the leading term in this square bracket will be 1, right, and you can have a similar expression for the Neumann function, which is a standard expression that you will find in any mathematics book, and you use these power series expansions for the Bessel function and the Neumann function, and then take the low energy limit z tending to 0. So, the Bessel function will go as z to the l divided by this term, and the Neumann function will go, there is a minus sign here. So, it will go as 1 over z to the l plus 1, right. So, let us first consider l greater than 0 terms. We will also consider l equal to 0, for which this term d is equal to 1, and this is the definition of this notation, in which 2 exclamation marks are used instead of just 1 to represent the product of odd numbers, and these are some alternative forms. You can stick in the missing even numbers in the denominator and compensate for them by inserting them in the numerator. Okay. You can do it for the second term as well, and from this numerator 2 will always be a common factor. So, you will have 2 to the power l multiplied by factorial l in the numerator. So, this is just some convenient way of writing this term. This is not of much significance, but only alternate and compact ways of writing this notation. So, notice that this product of these two double factorials can be written in terms of products of these factorial terms equivalently. So, you will either see this form or this form depending on what book you are looking at, but it is essentially the same term. Okay, so, this is just a matter of notation, and we come back to our analysis of the low energy behavior of the tangent of the phase shift, and we have found that this low energy behavior of the Bessel function goes as z to the power l, and of the Neumann function it goes as 1 over z to the power l plus 1. So, now to get the behavior of the phase shift at low energy, you need the Bessel function here and also here, and then you need the Neumann function here, and you need the derivative of the Neumann function here. So, you need not only the Bessel functions and the Neumann functions, you also need their derivatives, and these are the derivatives of the Bessel function and the Neumann function in the small energy region as k tends to 0. So, it is just the derivative of z to the l, which is l z to the l minus 1, and likewise over here you will get 1 over z to the l plus 2. So, there is a minus sign here and a minus sign here. So, that can be struck off, and these are the derivatives you get for the Bessel function and the Neumann functions. So, mind you, this is, there is a prime here which denotes a derivative. So, these are the derivatives of the Bessel function and the Neumann function, and these approximate derivatives which you have on the right hand side, which are reasonable approximations at low energy, they can be used over here in this expression for the tangent of the phase shift to examine the low energy behavior. So, let us put those terms in. Now, this is what you get. So, this is j prime. So, j prime is l z l to the minus 1 over d plus. This is j, the Bessel function, which goes as z to the l over d plus. So, you got 1 over d plus square in the numerator, and in the denominator if you plug in all the terms, you put the n prime, the j and the j prime and the n, you get 1 over d plus over here. Okay. So, with 1 over d plus square in the numerator and 1 over d plus in the denominator, you will be left with only 1 power of d plus in the denominator overall, right. And then you also have a d minus overall in the denominator. So, you get product of d plus and d minus in the denominator. In the numerator you have got this q minus 1 term which remains as it is. Then you have got a product of Lz to the power L minus 1 and z to the power L, right. And then you have got the rest of the terms over here, which is q times L plus 1 is coming from here, z to the power L, and then this z to the power L, and you also have an Lz to the power L minus 1 over z to the power L plus 1 over here. So, you can take z to the power L from the denominator to the numerator, z to the power minus L goes as z to the power plus L in the numerator, and then you are left with z to the power minus 2 in the denominator. Okay. So, this is just simple rearrangement of the powers of z. Z in our case is of course Ka. So, we know that the energy is a parameter there. So, this is the expression that you get. Notice that this phase shift goes as the 2L plus 1 power of Ka. Okay. That is the result which is emerging from this, and we will see it explicitly. So, this goes as z to the power 2L plus 1, and then you have got the remaining terms over here. Now, what is q? Q was defined as the ratio of these two logarithmic derivatives. The numerator is the logarithmic derivative for the free particle, the denominator is the logarithmic derivative for the case of interest in which you have got a certain target scattering potential. So, this is the logarithmic derivative for v equal to 0 for the, and then you can ask what is the value of this as k tends to 0. Okay, this is the free particle logarithmic derivative at an arbitrary energy, and it will have a certain approximate value as e tends to 0, as k tends to 0. So, this you can determine by taking the logarithmic derivative corresponding to the free particle, which is the Bessel function and its derivative, and you take the Bessel function, you take the derivative of the Bessel function, and you find that the logarithmic derivative for the free particle goes as L over A. Okay, that is the leading term. Okay, there are other terms and we can consider some of them as we need them, but this is the leading term. So, the leading term goes as L over A, and this means that Q goes as L over A and it is multiplied by 1 over gamma, because that is the definition of Q, right. So, we can put this value of Q, which is L over A gamma over here, this is Q, and this Q is replaced by L over A gamma. Rest of the terms are the same, which is L plus 1 over L plus 1, you have got z to the power 2 L plus 1, and then you have got the coefficient Q minus 1, but Q is L over A gamma. So, that is what is used here, right. So, now let us simplify this a little bit. So, this is L over A gamma minus 1. So, you will get L minus A gamma over A gamma, right, and you do the same in the denominator, and then you cancel the A gamma, and then the remaining terms which survive are L minus A gamma over d plus d minus product, and then z to the power 2L plus 1, and in the denominator what do you have? This L cancels this L. So, you have got L plus 1 plus this A gamma would have multiplied this 1. So, that is the term which comes here. And essentially we need the limit of gamma as k tends to 0. So, this limit is indicated by gamma caret, like putting a little tiny hat on top of gamma. So, this is the low energy limit of the logarithmic derivative, which is the term of interest. So, the tangent of the phase shift has a low energy behavior, k tending to 0 behavior, which is given by k a to the power 2l plus 1 L minus a gamma, this is gamma caret, which is the low energy limit of the logarithmic derivative, and L plus 1 plus a gamma caret. So, this is the overall conclusion, that the low energy phase shift goes as k to the power 2l plus 1. That is the overall conclusion which comes, other than multiplying factors and so on, but this is the dominant story which is emerging. Mind you, however, that there is a denominator here L plus 1 plus a gamma, and it could happen in some particular case depending on a value of L, because in the partial wave analysis you got all values of L. So, the denominator is not just a single value, you have got a similar term for each partial wave. So, for some particular partial wave, for some particular quantum number L, and if it happens for that quantum number, then you have to consider this term carefully, that if this term happens to be equal to minus of L plus 1, then this term is going to blow up and you will have some sort of a 0 energy resonance in this case, and that is something that we might want to consider. So, for the moment let us consider these situations, which is the non-resonant phenomena, and we will see what consequence it has on the scattering amplitude and the partial wave amplitude. So, partial wave amplitude is what goes into the scattering amplitude. The scattering amplitude, this is the Faxen-Halsmark resolution of the scattering amplitude in partial waves, partial wave decomposition of the scattering amplitude. Okay. So, this has got the S matrix element, which is e to the 2I delta, and let us consider, as we have been doing in this analysis, small tiny phase shifts for which delta will be almost equal to sine delta, which is almost equal to tan delta. Okay. So, for small angles, the angle itself and the sine and the tangents, they are nearly equal if you take the leading term in the corresponding power series of the sine and the tangent functions. So, tan delta or the phase shift itself goes as 2L plus 1, as we have seen, because that is how the tangent goes, to which the phase shift itself is very similar, and this is the S matrix element. So, this is cosine 2 delta plus I sine 2 delta, which for a small angle the cosine of this is nearly equal to 1 and the sine of this angle is nearly equal to twice delta itself, right. So, you get 1 plus 2I delta for small delta, which means that the S matrix element is nearly equal to 1 plus this 2I times the phase shift, and this phase shift we know goes as the 2L plus 1 power of k, other than some multiplying constants which I have written as C with a subscript L. So, this is the overall behavior, low energy behavior of the phase shift. So, the partial wave amplitude, so you have to subtract from this S matrix element 1, so that this 1 will go, and then this 2IC k to the power 2L plus 1 is divided by 2IK. So, you get the partial wave amplitude goes as k to the power 2L plus 1, because 2L plus 1 is divided by 1 power of k over here. So, this goes as k to the power 2L. So, the modulus square will go as 4L, and as L increases, as energy decreases, this will go very rapidly to 0. Okay. because you are taking the fourth power and not just fourth power. If L is equal to 1, you are taking the fourth power. If L is equal to 2, you are taking the 8th power. If L is equal to 3, you are taking the 12th power of k. So, it goes to 0 very rapidly, and the leading term will of course come from L equal to 0, which is why the S wave scattering is of so much importance. This hangs well with our understanding of the centrifugal barrier and everything that we have learned about the partial wave analysis, that you do not really have to consider higher partial waves, and it is the S wave scattering which is of most importance, but then of course other terms are also contributing, and the S wave scattering does play a very important role. And for the S wave scattering, it is very useful to define a parameter which is called as the scattering length, which I will now define. It is particularly useful in low energy scattering phenomena. So, let us define the scattering length for the S wave, and this is the definition of the scattering length alpha. Notice that it goes as 1 over k. So, it will have the dimensions of length, which is why it is a length. Okay. And this is the definition of scattering length. The partial wave amplitude we have seen is given by this expression, and if you now take the low energy limit of this partial wave amplitude, take these limits as k tending to 0, then you have this cancellation of 1 over here. This cos square delta is written as, you have got all of these sine functions and so on. So, if you just manipulate those, the trigonometry carefully, then this 1 cancels, and essentially then these 2 factor 2 cancels, and you are left with sine square delta minus sine square delta over here. But then again you deal with small delta, for which sine square delta will be ignorable. Okay, delta square is very small, and cosine delta 0 will be nearly equal to 1. So, this whole expression reduces rather simply to this I sine delta over I k, because cos delta is nearly equal to 1, sine square delta can be dropped. Okay, it is a small quantity, and you cancel the I over here, and this by definition is the scattering length. So, the scattering length, or rather its negative, is what gives you the partial wave amplitude in the low energy limit. Okay, that is why it is so important. Now, once you have the partial wave amplitude, you can get the scattering amplitude. And what is the scattering amplitude? If L equal to 0 alone is contributing, then this 2L plus 1 is equal to 1. AL of k emerges in terms of the scattering length. PL of cos theta for L equal to 0 is just equal to 1, right. So, essentially you get the scattering amplitude equal to the partial wave amplitude, which is equal to the scattering length with a minus sign, but you are anyway interested in the square of this. So, that gives you alpha square, and this of course is the differential cross section d sigma by d omega. Okay. So, this is the differential scattering cross section d sigma by d omega. If you integrate it over all the angles, you will get the total scattering cross section, which will be just the total solid angle, which is 4 pi times alpha square, which of course will have dimensions of length square. So, that is what we get, and let us look at this expression for L equal to 0. For L greater than 0, we have already looked at the expression for tan delta. We have seen that it goes as k to the power 2L plus 1. Now, let us see what it does for L equal to 0. So, for L equal to 0, you have explicit expressions for the Bessel functions which are exact. Okay. and you use these expressions for L equal to 0. So, the Bessel function is sin z by z, the Neumann function is minus cosine z by z. So, you can take their derivatives, okay, put z equal to k a and then put all those terms in this expression for the tangent of the phase shift, and once you put all of these expressions over here, gamma of course has to be determined. This can also be determined easily in terms of the Bessel function and its derivative in terms of the parameter q. So, q is going to appear in this expression now, because we are expressing the logarithmic derivative in terms of q. So, this is just a simplification with this gamma in the numerator and in the denominator replaced by this ratio, which is defined in terms of q. So, you simplify this expression a little bit, multiply by q 0. So, you get k j prime times q 0 in the first term, then you have got the numerator of the second term, but this j 0 k a cancels this j 0 k a. So, there is some simplification coming from there. You have only k j 0 prime, which is what you have over here. You do the same thing with the denominator and you have a rather straightforward expression for the tangent of the phase shift. So, this is the derivative of the Bessel function. Okay. Now, there is a k here and there is a k here. So, you will be able to cancel them, and now the derivative of the functions are also known, because you have the explicit form of the Bessel function as well as the Neumann function. Okay. So, you got 1 over k a and 1 over k a square in all the terms, either 1 over k a or 1 over k a square in all the terms. This is in the numerator and this you have got similar things in the denominator. So, it becomes useful to multiply and divide by k a square, okay, and that will give you a rather simple expression here. And here you have got expression like theta cos theta minus sin theta, theta being k a, and here you have got theta sin theta plus cos theta, okay, and here again you have got theta cos theta minus sin theta. But we have the power series expansions for sin theta as well as for cos theta. So, you using those you can get the expansions for theta sin theta and for theta cos theta and plug those expansions in and then take the leading terms. Okay. So, these are the expansions for the cosine and the sine functions. So, these are the expansions for theta cos theta and theta sin theta. You just multiply each term by theta in these expressions, and then here you need theta cos theta minus sin theta. This is where you have theta cos theta minus sin theta. So, that will have this theta cancels this theta, this one is with a minus sign and this is with a plus sign, okay, and the leading term in this goes as the cube of theta with a minus sign. So, this goes as minus theta cube over 3. Now, this is for theta cos theta minus sin theta. You do the same for theta sin theta plus cos theta over here, and this goes as 1 plus theta square by 2. So, you can insert these approximate expressions, retain the leading terms. The leading term here is minus theta cube over 3, keep the leading terms over here, and the cotangent can also be expressed in this series, and then you have to multiply the power series for cotangent with the cube of theta. Okay. So, that helps, and then once you take care of this, so when you multiply this with the cube of theta, you get square of theta with a 1 over 3 factor. Okay. So, you have to keep track of all the signs and the factors accordingly, and now that gives you an overall expression for the tangent of delta over here. So, you have got a Ka cube, but you have got a Ka square in the denominator. Okay. So, you can extract the Ka square as a common factor in the denominator. So, this term becomes minus 3 q0 times Ka to the power minus 2, and this Ka cube is divided by Ka square. So, you get 1 power of Ka. So, this is now in a form similar to the form we had for L greater than 0. Okay. So, both the forms, whether it is L equal to 0 or L is greater than 0, you will get an expression for the tangent of the phase shift in very similar form, and we will continue from this point in the next class. So, thank you very much. If there is any question, I will be happy to take. Otherwise, goodbye for today.